Okay, so for this lecture video, I'm going to explain to you the difference between resistors connected in series and resistors connected in parallel. So when current can flow only in one path as it flows through two or more resistors connected in line, as shown in this figure, so the resistors are said to be connected in series. So let's say this is my first resistor R1, second resistor R2, third resistor R3. So they are connected in one path. And one thing to note is that the current follows this one path, and therefore if I have this current I flowing through my resistors in series, then I can say that the current that will pass through R1 is the same current that will pass through R2 and R3. So I have only one value of current for this case. Also, for resistors in series, we don't have any nodes. So what do we mean by a node? So in electronics, when we say a node, so this is a point where three or more current carrying wires or branches meet. So for this case, I have three current carrying wire. So let's say this is the first wire, second wire, and third wire. And one thing to note about node is that your current will be divided as it passes through a node. So let's say I have this current I1. So my current I1 will be divided into two, current I2, then current I3. So by law of conservation of charges, or by your Kirchhoff's current law, which is I'm gonna discuss later. So your I1 is equal to I2 plus I3. Also, for resistors connected in series, the voltage drop for the resistors, for each resistors, uh, can be derived using our usual formula. V is equal to IR. So we know Ri, which is the same for all the resistors. Then we know the value of R. So lastly, for resistors connected in series, we can express it to a single resistor that will be called your R equivalent or equivalent resistance. So this is just equivalent to the summation of all the uh, resistors or the value of your resistances. So it's very simple. Several resistors are connected in parallel between two nodes if one end of each resistor is connected to one node and the other end of each is connected to other node. So for this scenario, for this figure, three resistors, so this is R2, then we have R3, both of their ends are connected to a node. So both of these parts is a node wherein my current will be divided. So let's say I have this current I. This current I will be divided into three. So let's say the current that will pass through my R1 is a certain current I1. Then the current that will pass through my second resistor will be called I2, the second current. Then I have this third resistor R3, then I will call the current I3. So therefore, again, by the law of conservation of charges, or later by the Kirchhoff's current law, my current, so the current I, is equal to I1 plus I2 plus I3. So this current is divided as stated here. So next, for parallel circuits of resistors, the equivalent resistance is always less than the smallest of the individual resistances. So as shown in this formula, the potential drop V across each resistor in parallel is the same as the potential drop across each of the others. So which means that for if in series, for series circuit, we have the same current. For parallel, we have the same potential drop. So the potential drop across R1 is the same as the potential drop across R2 and R3.